Number 13. We've got a reaction. They're giving us an initial rates data table. We know that this is what we're going to do to figure out the orders. So we've done something similar to this before, but this one I think has an interesting twist. So let's look for an experiment where there's something constant. So in 1 and 2, A is constant, so I can kind of investigate B by comparing what's happening there. And it looks like the concentration of B is doubling and the reaction rate doubles. So what that means for us is when we're drawing our general rate law, it is going to be first order in B. Now let's look at and see if we can figure out A. Well, in order to figure out what A is, I would like to have two experiments that are constant in B, and you'll notice it does not have two experiments that are constant. Now this is a multiple choice test, and you guys know that we could use the rate ratio method to figure that out, and a lot of times you can do that without a calculator. But you're kind of time limited here, so we're probably going to want to sort of estimate it. And so let's see what we can figure out. Well, the thing to remember is that B is first order, so we know that its impact change will cause it to double. So I'm going to compare experiments 2 and 3. We could do experiments 1 and 3. We just want to make sure we have a place where A is changing. And so let's look at experiments 2 and 3. You'll notice that B is doubling. And the rate of the reaction, you notice it doesn't double. If it were doubling, it would go from 4 times 10 to the minus 6 to 8 times 10 to the minus 6. But it doesn't. It actually goes to 16. And you might be saying, well, what do you mean 16? It says 1.6, but it's times 10 to the minus 5th here. So it's really like being equivalent to, 4 times as much. So A definitely is in our rate law. There is no doubt about it. And as a matter of fact, we can guesstimate it because the reaction would double just from the impact of the change of B. And so it'd go to 8, and then it's doubling again as we doubled A. So we are pretty darn sure it's first order in A. So your answer is going to be D here. Number 14. So they are giving us a table that's looking like one of those kind of half-life decay tables. After a certain amount of time, a certain amount of stuff is disappearing. And so they say reactant A underwent a decomposition, and they want to know which of these could be the rate law. So you notice we want to know, is it first order, second, first, and A, that sort of thing. And we have these little sort of multiplications of the rate constant in front. Now, the key thing to notice in our table is that if I were to sort of graph this data, let me graph it, sort of changing concentration over time, at 0 hours here, we'd have 0.4 molar. And after 1 hour, it had dropped to half that amount, right? It had dropped to 0.20. So we know that the half-life of this substance is 1 hour. And then after another hour, so if we go here, so this is 1 hour and this is 2 hours. After 2 hours, it's dropped to 0.1, so halfway again. So there's 0.1. And you notice it keeps losing half of its material each hour. So the half-life is 1 hour. You remember that decay pattern where you lose half of your material each half-life is the hallmark of a first-order reaction. And it turns out a lot of substances, certainly radioactive nuclei, all decay in this way. So if it's a very regular pattern like this, it'll be first order. So it's going to be either A or C, and it's A. There's no reason why you would multiply the rate constant times 2. So the answer is A.